All right, so this is homework 9, number 7. And essentially we have a diffraction grating that has 200 lines per millimeter, and it's illuminated by two monochromatic light sources with wavelengths lambda1 400 nanometers and lambda2 525. This is a two-part question. In the first part, we're going to determine the separation of the second order maxima on the screen, that is 2.5 meters from the diffraction grating. So we're gonna have to solve this equation. We're gonna need to solve for both the first order and the second order, because we're gonna need to find the difference between the distance from the center to the first one to then the difference between the center to the second one. And there's gonna be that in-between space, delta x, that we're gonna have to solve for. So I guess this one's kind of, just in respect to part A, I can see just from the top of my head that there's three parts that we should solve this guy through. So first, we should start by writing each of the equations we're going to use. So, sorry, I'm a little bit out of breath. I just had to run out and then couldn't grab something. So I'm panting and trying to talk. So first, we're going to have our two equations, right? So we're going to have d sine theta equals, I'm going to call that for angle 1, m1 lambda 1. You don't see that, yeah. And then for our second equation, we're gonna have d sine theta 2 equals m2 lambda 2. And I guess the first part of part A, I'm gonna call this part A, is gonna be solving for what that d would be, right? So we're given, how do they word it here? 200 lines per millimeter. So essentially what that is I'm gonna call that Roman numeral 1 to find d is just 1 over 200 times 10 to the third, right? And that also equals, did I write it? Yeah, 5 times 10 to the minus 6. Okay, and then Roman numeral 2, what we're going to do is we're actually going to work with our first equation, and we're going to pull out theta 1, right? Because what do we know? We know d, we know that it's the first order, and we know the lambda 1. What's unknown is that theta. So then Roman numeral 2, we're going to be solving for theta 1. That's going to equal sine inverse times, maybe let me take a step back here for 1 sec. It'd be easier to solve for theta 2, I think, actually. I'm embarrassed. Okay, I need to pause and think about this one for a second. Okay, so yeah, they tell us we're dealing with second order. I was wondering where that 2 came from. So yeah, we're dealing with the second order in respect to both of them, but the difference is the actual wavelengths, right? So lambda 1 versus lambda 2. I guess don't get confused by this notation as one of them was going to be 1 or 2. We're working with the second order. So, all right, sorry about that pause. I am resumed, presume. All right, so yeah, so then we're dealing with second order. So times 2, the wavelength, which is 400 times 10 to the minus 9. And then I'm gonna have to bring d to the other side. So I'm just gonna multiply by 200 times 10 to the third, like that. And then if you do all that, your theta 1 should come out to be 9.2 degrees. Okay, so let me just take a step back and explain why I had to pause. Let me explain 2 things actually. First is this is what we're talking about wavelength 1. So this subscript here is not telling us we're dealing with the first order, but we're dealing with the second order of the 400 nanometer wavelength, right? So don't get confused. I'm still plugging in a 2 here. The second thing is, the equation is normally d sine theta 1, and and I multiply by this on both sides, this 200 times 10 to the third, to cancel it out on the left and to put it on the right. And that's how you're going to get this angle, right? So using this angle now, we're going to be able to pull out what x1 equals. And that's going to be that distance from the center to the to the reading of the 400 nanometer wave. Okay. So with this information, like I said, we can solve for x1. So our x1 equals, we know what the length is, right? So that L tan theta 1, and we can just plug in everything. So that's going to be 2.5 tan 9.2, which should be equal to 0.405 meters. All right. And then now we can solve for x2. It's a little more involved, but kind of same principle. And that's just going to be using essentially the same equation, but I'm going to need to break it up a little bit more just because this one hasn't been really solved through. So I'm going to have L, right, M2, the lambda 2, divided by D. So essentially what I'm taking is, so I'm just going to take both of those values. So it's going to be, again, second order, okay. So the same distance, 2.5, so then times 2, except the difference now is that lambda is equal to 525 times 10 to the minus 9. And then this is all going to be divided by D, which we showed before is 5 times 10 to the minus 6, right? So then x2 equals 0.525. All right. So now we need to find the difference because what we're looking for is, how do they word it? Let me just say it. The separation between the second order maxima. So that's going to be like, this is how far from the center, this is meters, right? This is how far from the center the 525 nanometer wavelength second order peak is. And this is how far from the center the 400 nanometer peak is. So like lambda 1 and lambda 2, right? So we find that difference. I'm just going to write it right here. So delta x equals x2 minus x1, which will be equal to 1.2 meters, right? So that's that difference between them. Sorry, I kind of got a little confused here with my own notation, but I think that I kind of explained it there, where we're still dealing with the second order, even though I wrote M1. Okay, so that's part A. And then in part B, we're kind of asked for something else. Allow me to erase real quick. Okay, so then in part B, we're asked what determine the highest order for which the maximum is still projected on the screen. And then based on that, we know like to have the highest order, like the max, we essentially have to have theta equal to 90 degrees, right? Because sine 90 is equal to 1. And after that, like it can't be any more than 1, right? So we're going to set up both of our equations. So for M1, we're going to say d sine theta over M1. Oh, excuse me. I was like, what? M1 again. Lambda 1 is what I meant. And we discussed that sine theta is equal to sine 90, which equals to 1. So essentially all we're really dealing with is d over lambda 1. And then that comes out as 12.5. And then with respect to M2, like the highest order it could be, again, is we're going to say, I already explained why it's 1. So it's going to be d over lambda 2. And that's going to equal to 9.5. And now we have these two answers, right? So we have 12.5 and 9.5. The highest it could ever be is going to be choose the lowest one and then round it down. So the highest order will ever be is m equals 9, right? We can't be in between. We have to go to the closest highest one, which is 9, right? Even if this value is 9.9, like it's still not the order 10, so we still have to go to 9, right? So that's why we're choosing 9 here. All right, so yeah, I hope that makes more sense. I apologize, I got a little mixed up there for a second. I think the answer key for this one's wrong by an order of like 10 to the third, I want to say, if I recall correctly. So yeah, I think that this should clear that up. All right,